Welcome everyone, my name is Bartek and today we'll be talking about art of macro benchmarking. I would love to share a few information on what macro benchmarks are, how they are different to maybe other ways of assessing the efficiency that you know, and why you should do it now. My name is Bartek Płotka again. I work at Google and specifically in Google Cloud. I also do a lot of stuff in open source. I maintain Thanos and Prometheus monitoring systems, and I'm active in the CNCF space. Also related to this talk, I wrote a book called Efficient Go with O'Reilly, and some of the content of this talk is kind of presented in the book in much more detail, so you can feel free to check it out. So let's straight go into action. Why we would even optimize our software. And of course, we are in the P99 conference, so hopefully you already are convinced that we should optimize software, at least from time to time, but let's reiterate very quickly. I don't know if you watched an Apple event in September, but you know, when they're really good at marketing, they are really good at making products. And I don't know if you noticed, but every third minute, they have the word of performance. Like they talk about, you know, a new product or upgraded product about CPU and their efficiency and additional computing units and so on, right? So definitely it's important for them and for users apparently. And this is not a surprise, right? I could give you many reasons. You probably have a lot on your own as well. But, you know, for example, resilience, like your system, if it's constantly booming, getting out of memory or timing out, that's a problem, right? Like, so for the resilience purposes, you might want to optimize your software. Perhaps you want to compete with other solutions, be faster, have better user experience. So that's another reason. You want to maybe save money, right, on how much you use operationally. That's also kind of a very good reason to optimize. And finally, to avoid, you know, sometimes a huge scalability problems or even distributed systems at all. Like sometimes reducing the wasted cycles or wasted memory for your software is as easy as that to avoid those problems. And I could give more reasons, but there are also excuses why we might not want to optimize software, right? And let's bring one excuse is, you know, maybe the hardware is getting better and better, and we are, you know, improving it over time. And of course, maybe our application has more data over time as well. Maybe the hardware optimizations are kind of getting us ahead, so we don't need to touch our code and really care about, you know, efficiency of our software, right? And, you know, like from the Apple event, we learned that, you know, there is a new processor, new chip with integrated units, and it's magnificent, it's kind of like fast and so on. However, the truth is, if you go into details, that little improvement has been made to important factors of your hardware, right? For example, random memory access or single CPU core frequency is really the same across many years, right? And it's not getting any better due to physical limits like thermal aspects and so on. And what caught my eye during the Apple event, you know, they mentioned that they have this many transistors. They're super small. Some parts of it are as small as 12 silicon atoms. And like when you think about it, like there are not many atoms left to make it smaller. So it's kind of hard to expect more processing unit, more units, more transistors within our chips within the same size going forward, right? Because like we cannot make it smaller. It's just how many atoms it would use, right? So this speaks that we have to care about efficiency. So how to do it effectively? Well, I like to kind of draw this process. I call it TFBO. It's in my book as well. Test, fix, benchmark, optimize. It's kind of very straightforward. It gives you a hand in what steps you should do, ideally, to have effective development process that includes some efficiency aspects in pragmatic way, right? So first of all, you want to test and make sure your workload is functionally correct. That's kind of like the first thing, even before thinking about any efficiency aspects. Then, ideally, before even optimizing, you would like to know if you have to optimize at all, right? And what's the current level of the efficiency? You know, is my latency good enough? Is my memory usage kind of like low enough so I can accommodate it in my clusters? Maybe CPU cycles, is it, like extensively high, too many of them, or just good enough? And what is the overall cost? Like all of this you can tell before releasing by benchmarking, by assessing your efficiency. And finally, that decision gives you, some kind of input if you can release or not, or you should look into some optimizations, right? And first, you could gather some information from those benchmark and assessments to perhaps find bottlenecks. And you kind of keep this process, right? And what I want to talk about today is this benchmarking part. So assessing efficiency, right? That's kind of one of the most important and difficult to do. And one way of doing this is to just think about your system, your program, like statically analyze this. That kind of gives you some kind of rough numbers of, what's the complexity of your algorithms, how large your data structures are. It's really difficult, and sometimes like you cannot talk about like specific milliseconds it would take, but it gives you some sense of efficiency. But there might be better solutions, right? What about some empirical kind of experiments that gives you this data, evidences when on your efficiency level for your software on certain environments, right? And that's what we call benchmarks. And we can kind of split them into multiple categories. I like to split them into micro benchmarks, macro benchmarks, and production benchmarks. And it's really important which one you have. And usually you can have all of them or like some pieces on each of those categories and take whatever you want based on your use cases. So let's go through the micro benchmarks very quickly. So this is the kind of the simplest benchmark you could do. It's usually on the single unit level, on your function level or code statement. And many languages have built-in tooling for that. For example, Golang, you have this like command that you run, go test, and it kind of runs this one benchmark multiple times to ensure reliability of test and gives you some results, right? It gives you operations per second or like seconds per one operation, so latency of the operation. It do this multiple times so you can ensure it doesn't deviate, it's stable, and even allocations. So all of these are very accessible, quick feedback loop, but there might be problems. Like for complex application, you would need to create so many of them and run so many of them to really understand the overall performance of your multiple microservice application. On top of that, like those functions might integrate in surprising way. So you might want to kind of go higher level to assess the efficiency, right? So one way of doing this is benchmarking on production. Like you could just deploy a new version of your application, run it, and see how it interacts with production users on production load. That's kind of like the most true information of your efficiency level. And it might be good for your use case. It might be totally a good way of learning about efficiency of your software. But in majority cases, it can be dangerous, of course, because you might release a new version that has some bottlenecks, maybe running out of memory very quickly, and you cannot scale it quickly enough. So unless you do some canary deployments and so on, you might kill your production and create some incidents, some friction for users, right? So it might be too late. The feedback loop is also very, very, very slow. So, but the benefits are that you don't need any other environments, and you can use observability tools at hand that you use for normal monitoring operational SRE processes, right? So I want to teach you today about micro benchmarks, so something in between, where it's kind of like an experiment, deployment that is very, very similar to production, but it has some elements that are kind of simulated, right? So for example, instead of real users that might be impacted, you just generate the load in some way that user, in a similar way as users would do that. For dependencies, maybe you mock them. But the beauty of it, ideally, is that you use similar, underlying hardware, maybe similar cluster, maybe similar environment, maybe the same observability tools as well, which I would really recommend, because you can use the same observability tools that you use for debugging and monitoring for benchmarking result analytics. And I will show you how. So this is what this summary could look like, and this is what I kind of presented in my book as well, is that you could compare macro benchmarks and production benchmarks into functional testing, because at the end, benchmarking is just testing performance and functionality. So micro benchmarks are kind of similar to unit tests. Macro benchmarks are kind of like integration end-to-end tests, and production benchmarks are kind of production testing on production. So all of them have their pros and cons, and you might take, bits of each of those and implement in your own production, in your own kind of like development process. But today we're talking about macro benchmarks and how to get the most out of it. And the best is to learn from specific examples. So I'd like to introduce to you a PromBench, which is like a open source framework that we use in Prometheus system. And Prometheus is just a monitoring system. It gathers metrics, it allows querying and alerting. You might be familiar with it, and I maintain that. And we kind of created a framework that allows benchmarking it on the fly. What I mean by that is you essentially kind of develop on Prometheus. For example, someone updates code, propose a code with pull request on GitHub, and it proposes it with some feature change, right? Let's say it kind of hits, or like it's connected, it changes the hot code, what we consider that, a path in the code that is commonly used, for example, like our storage. And so we are unsure if, this is not impacting efficiency of Prometheus. So what we do, we kind of like invoke some command, and we talk to this prombot, and it essentially starts the benchmark. And with this benchmark, it gives very few useful links to observability tools that you can use when the benchmark finishes, or it's during the benchmark process. For example, you can check metrics through the Grafana dashboard. You can see the overview of we pre-built certain views that we are interested in. For example, how many series we have, how many certain expensive operations like compactions we have, how long they took, and how long queries are taking, how long append is taking. Those are very specific. They should be very specific to your application, but you can kind of build that on your own. We have continuous profiling, so we kind of can check, the profiles of the applications every 15 seconds. It gathers those, so you can kind of check that within this moment, for example, the allocations were made by this function, or the most CPU cycles were used by, for example, some hashing or so on. So this is super useful, and actually you should have that exactly on production as well, like a suite of those observability tools that helps you analyze the results, not only for debugging purposes, but here for benchmarking purposes. And thanks to this tool, we can make meaningful decisions. For example, in this case, my colleague Brian just found out from the dashboards that the memory, the RSS metric is a little bit higher for the new change. So then we dive into profiles or other tools and code, what it could be, the footprint of that, and if that's even a problem, because perhaps this percentage memory higher is useful, still kind of good enough for such amazing feature that we want to merge. Or maybe this is the trade-off for lower CPU, which is the current bottleneck. So, that's not necessarily a wrong result, or like the result that rejects this PR, but it gives meaningful data for the decision. So the key aspects that we have to think about when doing macro benchmarks: cost, right? Like for sure, everything has to be in the context of the cost, right? Like it takes time, engineering times you have to pay for performing benchmarking and analyzing this. Like PromBench is automated, so it's kind of taking that a little bit away, which is beautiful, which is what I recommend, having some framework, having some useful automation, but generally it can take time, so you have to be mindful. But it also takes time to maybe have wrong conclusions, right? Maybe you made a benchmark wrongly, so it shows that there was no regression memory usage, but actually there is. So this is also what you have to be mindful. Like having a benchmark that lies is also probably worse than having no benchmark. Finally, compute. And for example, PromBench, we have a cap because it's a Prometheus, it's an open source project within the CNCF, and it's CNCF sponsors, Google Cloud bill to $1,000, per month, which is not a lot, but it gives us opportunity to do what we want with basic standard benchmarking, like standard use cases. Next thing, reliability, right? We really want to make sure that our benchmarks are repeatable, so we can trust them, right? So it cannot be on unstable environment. It cannot be on your laptop while you are doing something. It cannot be on noisy neighbor environment in the cloud. You have to be kind of smarter than this. So what we recommend, or what we do in the prom bench, we perform this kind of like a comparison benchmark. So we run in the same time like Prometheus as a reference Prometheus and the Prometheus we want to benchmark, right? So thanks of that, we can compare and say, okay, this is, this change introduced like a memory leak, so we can see like a different memory usage, for example. And this is much better than trying to figure out the absolute numbers of like, oh, Prometheus for 10 million metrics uses 30 gigs of memory. Sure, that's maybe true for this particular environment, but for other environments, that might be totally different, because maybe the metric have a different characteristic, so that the payload has a different characteristic, and this kind of very complex space. So it's much better to kind of compare the same workload, the same traffic, the same payloads onto the same kind of pieces of software deployed to, for example, we deployed to the same cluster, just on different virtual machines, and kind of compare them. It's much more reliable like that. Speaking of isolation, like containers are not sometimes enough. We want to be on a safe node, so we essentially have a different node pools, and we use GKE and Kubernetes to manage all of this, and we just run Prometheus as the only container, except of course Kubelet and important Kubernetes workloads on one virtual machine. So we have Prometheus on one virtual machine, another Prometheus reference on one virtual machine, and then another virtual machine for everything else that automate this cluster, for observability tools, and so on and so on. So it gets expensive, but if you balance this out, you can fit into some reasonable bill and still have this isolation that is super important. So those Prometheuses that are benchmarked in the same time, they don't impact each other. And here you can see the node pools in GKE, and it is kind of like, maybe it's wasteful, but it's kind of like useful to isolate your workloads, and it's not that expensive as you might think, if you clean those resources after and you have automation to manage it all. And the last one, automation, which I mentioned already. We have like a GitHub bot and GitHub Actions that kind of listens on those commands and kind of like really kubectl apply certain node pools and certain kind of like resources, and then tear them out. It's super simple, no like magic GitOps, whatever. So it's it's kind of like super simple, and this is what you need. It's good enough for this. Relevance is another aspect, right? We want to make sure that we are simulating real workloads. So we use Case 6, for example, project, which is open source as well. And we also have like web servers that kind of simulate real metrics. So it's not like maybe artificial metric using, for example, Avalanche. We try to have it simulated as a normal web server, so, which is hard to simulate, but we do our best. Finally, observability, right? So we want to ideally have the same observability as production. So once you run the test, we have useful links you can visit and analyze observability signals. And we deploy, for example, Prometheus with some exporters. So we have a meta Prometheus that monitors other Prometheuses. We have Promtail with logs using Grafana Loki project. And we have a Parka. All of them are open source project. And Parka is for continuous profiles. So it kind of pulls the profiles every for example, 15 seconds, and we can kind of view the really, really important information over time. And all of this should be the same observability as in your production. Okay, to sum up, some lessons, some reminders. Make sure you understand FBO process. It's super useful. Use micro benchmarks. Remember about cost, reliability, relevance, and observability. Look on those open source projects that are really good and get you far. And really good, check the Prombench framework. Maybe it's open source, it's fully available on GitHub, and you can extend it, you can fork it, you can apply it to your application, not only Prometheus. For example, for our kind of Prometheus-like workloads, we just forked it and kind of like reused a little bit. So we use kind of, for example, Google Cloud observability tools for monitoring this. But anyway, it's kind of the same framework. So really look at it, check it out, and maybe it will be useful for you. Thank you.